Hi, I'm Dave Rich, and I'm a methodology expert with Mentor. I'm going to talk to you about the Verilog basics behind Systemverilog constrained random verification. And why is this an important topic? Well, the motivation is we're seeing a lot of people spend more time in debug than any other project task. And that's more than the planning, development, and running tests. And a significant part of that debugging time is spent dealing with constraints. So in my agenda, we're going to cover an overview of constrained random verification for those of you who may be new to this topic. And then we'll go over the Verilog rules for evaluating expressions. And then finally, we'll go over the effect that probabilities and statistics have on the results that you get. If we take a high-level view of constrained random verification, what we're doing is defining stimulus at a high level of abstraction. We're creating a random space, and then we're defining constraints or a set of system constraints that define all the possible scenarios that we want to stimulate our design. And this can be more efficient than individual directed tests, but you can of course complement a mixture of this by having random tests and directed tests in your verification process. But anytime you have random constraints and random stimulus, you need an automated way of checking your results, and you need to assess exactly what you've tested, and we call that metric-driven verification. So typically we use functional coverage to figure out what have we actually tested against our plan of verification. So if we look at a sort of a raw example of what a constraint is, here we have two variables, x and y, and the constraint we want to generate to is x less than y. So the brute force way of doing this is randomizing x, then randomizing y, and then seeing if x is less than y. And if it's not true, we'll try it again. And we'll just keep doing this over and over again. This can actually waste a lot of time randomizing and then throwing out the invalid results. Imagine if you had a large set of equations. And you may never reach a solution. It could be that your constraints don't have a solution, or it just takes too long. The probability of getting a valid solution is so low that you just may never see it. You can take an approach of creating random variables in a sequential order if you know their dependencies. So if I know that x has a value between 0 and 2, and so whatever I choose for x, I know that y has to be x plus 1 to the value of 3. But this gets very complex when there are more constraints added. So for example, if you had the least significant bit of x is not equal to the least significant bit of y. So this becomes much too difficult. So what a constraint solver does is it takes a set of random variables and a set of constraint expressions and feeds that into a constraint solver. And what the constraint solver does is it figures out a solution space, and it will figure out all the possible combinations, or it will generate a failure saying I can't find any solutions for this. And then once it finds the solution space, it picks a solution, and you can randomize many times, and it's basically what it's doing is picking different solutions out of that solution space. Now the way Systemverilog does this is it ties randomization to the object-oriented class system. So we define a class and we declare random variables. So here we have address and data declared as with a rand keyword, and packet number is another class member, but it will not be randomized. Then we add a set of constraints. And for example, two least significant bits of address need to be 0 when I randomize. Then we call the randomize method on this class after constructing it. And the randomize method will return true if it found a solution, and it returns false if it doesn't find a solution. So one thing to remember is that you should always test the result of the randomized method. And there may be a variety of reasons why you might want to do something and change your course of stimulus based on the randomization not succeeding. So let's take a look at that example with the two random variables x and y again. And so we have the constraint x less than y in our class, and we can see that there are 6 possible solutions. Now the solver will go about using some kind of formal technique, which we don't really need to go into here, but whether it actually builds a table or just creates a mathematical model of all the possible solutions, it really doesn't matter. What you just need to know is that there's 6 possible solutions here. The constraint solver will pick the random variables as a set. So it might choose x1, y equals 2. And each solution has an equal probability of being chosen. So out of these 6 solutions, we see that x has a 50% of being 0. Now, let's get into what Verilog expressions has to do with constraints. And in order to do that, we have to sort of go back and understand where Verilog came from. It started out unifying behavioral languages with RTL, gate level, and test bench all into one language. And that worked well for a while, but eventually what happened was there were a lot of demands on the test bench. So what happened is a lot of other language started coming out, and it split into a design component, a test bench languages, and there was another language for assertions. And the Systemverilog project came into being to join everything back together. And one of the fundamental principles of Systemverilog was to unify expression semantics, so that when you wrote 2 times 2 plus 1, that's understood to be 5, not 6. And we'll get into those semantic rules in a second here. So let's take a look at what's so special about a Verilog expression. I think the biggest part of a Verilog expression that it must handle specific integral bit widths, whereas most programming languages consider only bytes or words. And so you have lots of expressions dealing with different bit widths, and that all has to get reasoned into the operations. And also a part of that is dealing with signed and unsigned arithmetic. There has to be precise rules for these expressions so that synthesis tools know exactly which kind of hardware to create, and we don't want a lot of extra hardware created when it's not needed. So that's why bit width is very important. And there are many steps in evaluating an expression. We have to look at context, which is where an expression appears in relation to other expressions that it's a part of. There's the precedence rules, which operators we look at first. And so, for example, we have A plus B, shift C plus D, and we need to know that the shift operator has lower precedence than the addition operator. So this gets evaluated as A plus B shifted by the value C plus D. And there are casting rules of when we have different types, and whether we have signed and unsigned, different bit widths, that all has to get rationalized. One of the problems is that design and verification engineers are not really trained in software development, and you can see that by the fact that they avoid documenting what their code is supposed to do and what their intent is. So there's a lot of implicit defaults within Verilog that carry on into the Systemverilog language and then into the constraints. So let's talk a little bit more about what an expression context is. At the highest level, there's what's called a self-determined expression, and that's where the bit length and the sign of that expression has no external influence. And we typically see that at the top level of an expression. And there are other places we'll see in a moment where that can occur. Then there are context-determined expressions, and that's where the bit length or sign of the expression is influenced by being part of another expression. In this table from the LRM, we see a bunch of operators. For example, the arithmetic operators a plus j or a minus j. And these form a context, and the result of these expressions will have the size of the largest operand. And I and j will get sized to the size of the largest operand. We also have the shift operators, the left shift and the right shift. In this case, whatever the size or type of I is, that's the result. But j is going to be a self-determined expression, so I has no influence on how we evaluate j. And so this is a case where we have a self-determined expression j within another expression. And then there are the relational operators, I less than j, or I less than or equal to j, and so on. And these expressions all have a 1-bit result. However, the size of the operands get extended to the largest operand. J will get sized to the size of I. And then there's precedence. We know that the arithmetic operators have a higher precedence than the shift operators, which have a higher precedence than the relational operators. So that means when we see the expression a plus b shifted by c less than d, we know that because of the precedence rules, we're going to evaluate the addition first, followed by the shift, followed by the less than relational operator. And all of these operands, A, B, and D, will get sized to the largest operand, and C has no influence on the rest of the expression. It's a self-determined operand. And the Systemverilog LRM has all this information about every single operator, what its precedence is, and what the context of each operator is. There's no need to memorize this entire table. You just need to remember where it is in the LRM. Now let's see how bit width determination works. In a little bit more detail here, we're going to define the variable a as a 3-bit variable and b as a 4-bit variable. C doesn't really matter in this case what its size is because it's not involved with the context of the rest of the expression. And D will give it a 4-bit value. That means that all of these expressions will be sized to the largest operand, which is 4 bits. In this case, A will get padded with a 0. Also to note that the result of A plus B is evaluated in a 4-bit context. Any type of overflow that we have gets truncated. So if we're adding 4 plus 14, since we only have 4 bits for that result, we're going to get 2, and because we can't see the value 18, that 5th bit is going to get truncated. And that the shift right result is 4 bits, so we've lost that extra 5th bit, and just a 0 will get shifted into that position. Finally, the overall result of this expression is a 1-bit value. So if we really want more bits involved in this expression, we have to increase the size of our variable to 5 bits, or we can use a Systemverilog casting operator. Now let's see how this all applies to constraint expressions. So here's those same variables in a class, and we define A and B as random variables. We'll just keep C and D as non-random state variables, so they're effectively constants. If I have the constraint A plus B shifted right by 1, must be less than D, so I expect that to be less than 8. But as we just saw in the previous slide, that if we had 4 and 14 being added together, that's going to produce a valid solution. So we need to apply the same kinds of fixes by adding an extra bit to our addition or changing the size of one of the operands. Any one of those will work. Here's another case where the bit width is an issue. There is a sum method on an unpacked array, and what this does is sums all the elements of an array. In this case, we have an array of bits which are 1 bits, so the sum of 1 bits is going to be a 1-bit value, and so that's going to quickly overflow, especially if we have an array of 100 bits. We're only going to get a 1-bit result. The solution to this is to use the with clause of the sum method, and what this does is it casts each element of the array into an integer before adding it to the sum. So it's effectively the int of array 0 plus the int of array 1 and so on for all the different elements. That can have a value of 100. Now let's turn our attention to signed expressions. The signedness of an expression affects how it gets extended or padded with zeros, and it also affects relational operators. It's important to note that addition and subtraction, or the arithmetic operators, is always performed with 2's complement arithmetic, and the signedness of an expression does not matter. When you write a decimal number like 1, 23, 46, those are all considered 32-bit signed values. But when you write it as a based literal, like tick H1, that's considered unsigned. Or 64 tick D23, that's a 64-bit decimal 23. And expressions are unsigned unless all operands in the context are considered signed. So as soon as you have one unsigned operand, the whole expression becomes unsigned. And when you do sign extension, it only applies to the signed part of the expression. So let's take an example of this. Here we have 2 variables, A, which is signed 3 bits wide, and a unsigned variable B, which is 4 bits. So in this expression, we have a 3-bit variable A plus a 4-bit variable B compared with the 32-bit value 14. So A plus B will be evaluated in a 32-bit context. However, the signed part of this expression is limited to 3 bits. We're not going to sign extend A all the way out to 32 bits. A becomes an unsigned 32-bit 7. So 7 plus 14 is 21, and so 21 less than 14 is false. Here's a more interesting case where we see a constraint of an integer address less than 256. And all the built-in types int, byte and variables declared as signed can hold negative random values. When we randomize this, we're going to see unexpected, what look like large values for address, but they're valid because they're considered negative numbers. In this case, 256 is a signed value. So let's go over some solver bad behavior issues. We've seen some examples of getting results that are not what you expected. And we've seen how the expression semantics are the most likely cause of this. It's also possible to not get any results. You get constricting constraints or over-constrained constraints. And so the expression semantics are one possible cause of this. But let's talk about another area where you're getting valid results, but some results are missing. So you're not getting all the values you expect. That's where statistics of the solutions or solver ordering of how it picks values comes into play. So let's go into talking about the solution space and how probability and statistics affects the results. So we're going to take that example where we had x less than y, and we're going to add one more bit to the variables, so we have two 3-bit variables. As we said before, all the possible solutions have an equal probability, but if we look at the values for each of the variables, they don't have the same probability. So now we have 28 possible solutions. And when y is 7, for all those solutions there are 7 possible values of x. When y is 1, there's only one possible solution for x, and that's x equals 0. So if we look at the probabilities of x equal to 0, we see that there's 7 out of 28 possible solutions where that's true. And the probability where x equals 6, there's only one chance in 28. And similarly for the probability of y with equal to 7, there's 7 out of 28 solutions, and y equals 1, we have 1 out of 28 solutions. So if we want to get a even distribution on y, we can add this construct solve y before x. And what this does is it tells the solver to pick a value for y first and then pick a value for x. Now this construct has no effect on the solution space. We're still going to have the same set of solutions, but the probability of the values we get for y are going to change, and we're going to have a uniform probability of choosing the values 1 through 7. So the way I like to think of this as saying pick y's value from the solution space before we pick x values. So it's not really solve anything before anything else because everything is already solved. And it's important to note that the probability of x equals 0 goes up higher and the probability of x equals 6 goes lower. There's no way to get equal probabilities of the values of x and y simultaneously, so you have to choose one over the other. Now, with a small solution space, this distribution might not be a problem, but here's a more realistic case. So we have two random variables where we have a 1-bit variable and a 32-bit variable data. And we have this constraint: whenever control is true, we want data equal to 0. So again, the solver has to have a uniform distribution. And this sort of looks like if control is true, data equals 0. So it sort of implies that we have an ordering, but there really is no ordering to this constraint. They're all solved together. And this implication is turned into this Boolean expression, not control or data equals 0. And if we look at these possible solutions, there are 8 billion combinations of control and data, but only one solution where control is 1 and data is 0. So that means the probability of control being true is 1 over 2 to the 33, which is practically 0. We use the solve before constraint to fix this, and that gives us an even distribution of control being 0 or 1. We also have to remember that since data is now determined by control, there's a 50% chance of data being 0 and a 50% chance of data being not 0. Here's another example where we have an enumerated type that has 3 possible values. If we look at this, we can see if we didn't use the solve op before data construct, then the probability of no op would be about 1 over 300. Putting the solve before data construct gives us an equal probability of read, write, or no op. But sometimes we don't want this. We'd want a different kind of distribution. And so there's this dist constraint where we can actually tell it what we want the different weights to be. So here we've given read a weight of 20, write a weight of 15, and no op a weight of 5. So this means that read will have a 50% chance of being true, write has a 40% chance of being true, and no op has a 20% chance of being true. Another problem that I see is that people expect to get exactly the probabilities they specify. So for example, if they flip a coin 10 times, you expect 5 heads and 5 tails. But in fact, if you work on the statistics, you actually have only a 25% chance of that happening. So there are a bunch of tricks that you could do to get an exact probability. So assuming if you knew that you were going to toss a coin 100 times and you wanted exactly 50 heads and 50 tails, you could do something like what I've shown here. So we're using the RAND-C construct, which means to cycle through all values of scale that are available to it before repeating a value. So we'll cycle through all the values between 0 and 99 randomly before repeating. And so if we have these two constraints, if scale is less than 50, then toss equals heads, and if scale is greater than 50, toss equals tails, we know that we'll get 50 heads and 50 tails. So in summary, we've seen that the rules for evaluating constraint expressions must match the same rules for synthesizing RTL expressions. It's all one language. So you need to understand how to parse the context, the precedence, bit widths, and signed arithmetic in expressions. And finally, you need to look at the probabilities and statistics in your results to see if you're getting or missing particular sets of results. I've included a few references. Of course, there's always the Verification Academy forums and a few other DVCon papers that I've listed here. So thank you very much for your time.